excited to welcome Steve Chien, who's the head of Artificial Intelligence Group, JPL at NASA. Steve is going to be joining us via Skype from Pittsburgh to present on developing AI for future exploration of extraterrestrial subsurface oceans, the search for life on Europa. I didn't think I'd be saying that at this hour. Steve from Pittsburgh, are you with us?
Yes, I'm here. I apologize for not being there.
Well, welcome to Amsterdam. We've got a room full here, so I'm going to take it over to you. Welcome.
Oh, fantastic. Today I'm going to be talking about artificial intelligence in space and the search for life beyond Earth, specifically in under-ice oceans. So AI in space got a big boost in 2003 when we were given authorization to upload AI software to control the Earth Observing 1 mission. What did we use this AI software for? We used it in two main purposes. One is to analyze imagery data on board and detect high-level science events such as cloudy images, or as we're going to see upcoming here, an active volcanic eruption. We also use this AI technology, this machine learned classifiers, in order to track flooding and growth and retreat of ice caps. What's better than AI software to control one spacecraft? AI software working together to control multiple spacecraft. This video shows one of our use cases where we link together spacecraft in a sensor web where a detection of a forest fire from one spacecraft could be passed on as a message to another spacecraft, and that other spacecraft would then respond by tasking itself in order to acquire imagery of that forest fire, perhaps with a complementary instrument or a higher spatial resolution. And this kind of software was used to track flooding worldwide, to track volcanoes erupting worldwide, and was very effective at using AI in order to better observe these different phenomena. What are the different kinds of machine learning we use? Well, the simplest form was Bayesian thresholding, where we select on specific spectral bands, so such as red, green, blue, or even the other spectra that the instruments might be able to see in order to separate between the classes. We also use support vector machine learning techniques for over a dozen years on board the EO-1 spacecraft to track the growth and retreat of ice caps and freezing and thawing, and also to track flooding. And these techniques were actually more effective than the best human-derived classifiers. One of the most powerful demonstrations of this technology was to detect sulfur at Fjord, which is the northern area of Canada. And this is actually very similar to sulfur that we might see on an icy moon, like on Europa. And that sulfur might be indicative of an ecosystem which could support life. So that's very exciting. We used random decision forests to classify clouds and other objects. And we did hyperspectral onboard hyperspectral unmixing, which is figuring out what the minerals or substances that you're looking at that would form the signature that you're seeing. This allows us to pick out, again, very subtle signatures in a model-based fashion, not just a database fashion, such as machine learning. We also use unsupervised learning. This is basically looking for outliers, things that don't fit in statistically, and in this particular visual outlier technique, in this rural scene in Thailand, the buildings stand out. This is very important if we don't really know what we're looking for. And then we use machine learning to, in effect, create new sensors. In this case, we actually train the classifiers to look at volcanic images and pull out the plume, the shadow, and the land. And then we use geometric information about the location of the spacecraft, the relative location of the sun, the illumination, and we use geometric reasoning to figure out how high the plumes are based on the size of the shadows and the geometric information. This is very important because we're able to construct this plume height sensor, in effect, from a vision sensor, and plume height is very interesting to scientists because it's a proxy for how vigorously the volcano is erupting. Once we have all of these detections from the AI software, we have a scheduling system that tells us that allows us to determine if we can take different observations and to allow us to command the spacecraft by just telling it to take observations. We don't have to know, where the spacecraft is pointed necessarily when it's overflying. The software will figure out on its own and knows when to downlink the data and make sure we don't override our buffers or overheat the instruments or anything like that. So we learned quite a few lessons in deploying this software. One of the lessons we learned was to plan for success. Originally, we were just supposed to fly for 6 months. Just as a technology demonstration, we ended up being operational software used to command the spacecraft, to operate the spacecraft for over a dozen years. That was very important. The second thing we learned was continuous improvement. The sensor web, we started out with just linking together a few spacecraft and a few ground sensors. And we slowly built that up year by year until finally, after about a dozen years, we had 20, 30 different assets all working together. This was very important. Another thing we learned is reliability. In order to get reliability, we had to have a layered architecture. And so we actually had a planner, we had an execution piece, we had the base flight software, and all of these worked together. So if one area, didn't catch a problem, it was caught at a lower level, and this, in the end, made for a much more reliable system. We also rolled out this system incrementally in order to make sure that it would work reliably, because the spacecraft is a very expensive asset. Unfortunately, the Earth Observing 1 mission ran out of fuel, and in 2017 we had to decommission the satellite. However, you don't need to feel sorry for us. We've been on to bigger and better things. Specifically, the Mars Science Laboratory rover has on board autonomous targeting software. This software allows it to select its own targets for the ChemCam laser, as well as other narrow field of view instrumentation. This software allows the rover to select science targets according to science specifications and fire the laser to acquire imaging spectroscopy information about the resultant, about the targeted rocks. Back before the system, which is called Aegis, the scientists had to manually acquire the images, downlink the images, select the targets, figure out which targets to have subsequent imaging on, and then figure out the commands necessary to target these particular targets. Now, the onboard rover software, the Aegis system, performs all of those tasks automatically, including checking to make sure that we don't fire the laser and hit the rover, because that would be a very bad thing. This has been very successful, and this software enables the rover to take many more science images than it previously was able to acquire. And we're very excited that the next rover on Mars, the Mars 2020 rover, will have an even more sophisticated capability to detect different target regions and actually take measurements at what are called the contact regions, which are taking measurements across the boundaries between these different regions. One of the lessons that we learned from this work is that what we're interested in is the confluence of artificial intelligence, operations, and flight software. And so one thing that's been instrumental to the successful deployment of the software is that we have people who have spent time in all of these 3 different areas. In fact, we purposefully rotate people through these areas, and this is one of the lessons learned to deploy AI systems, to understand both the software implementation, the operations, as well as the AI components. As I said, the next rover, the Mars 2020 rover, is going to have even more sophisticated artificial intelligence on board. Specifically, it's going to have a scheduling capability that allows it, such as in this execution of a plan, when a plan takes longer or shorter than expected, it can adjust the remaining parts of the plan, as we're seeing here, in order to take advantage of that, to do more science or perhaps conduct measurements at a more advantageous time. And this is, in fact, the scheduler at work here, where as it places the activities, these bars at the bottom tell you the different constraints that are forcing the activities to be placed at particular times. And then that line, this line here, is actually showing the power. This is the minimum power for this all that make sure that the rover can properly execute this plan. One of the other lessons that kind of echoes what I said earlier is it's very important to focus on the operations processes in order to know what kind of validation is needed and what kind of software is needed, AI software is needed for the overall process. So in the rover planning, there's actually a look-ahead planning where you look ahead a few Martian days or sols in order to figure out what general high-level activities you want to do. Then there is the ground planning, which uses both the activity dictionary and plan component libraries to develop the tactical plan. That's passed uplinked to the rover where the onboard scheduler executes and reschedules that as is appropriate. And then after that sol of execution, we actually have to use a lot of the same tools in order to understand what the planner did on board. So as you can understand, this is a very complicated operational process, and it's very important to understand it very well in order to understand how to infuse the artificial intelligence technology into the overall process. Artificial intelligence scheduling was used to help support Rosetta science operations at the comet Churyumov-Gerasimenko. Artificial intelligence scheduling is also used to operate NASA's Deep Space Network, a network of communications antennas used to talk to all the spacecraft beyond Earth orbit. This is used in long-range scheduling, mid-range scheduling, and near real-time scheduling, and even takes into account the operator load. The Mars Target Encyclopedia uses artificial intelligence to study large numbers of scientific articles and figure out which concepts are interrelated. For example, target locations on Mars, and elements or minerals, science topics. And this allows the scientists to use the Mars Target Encyclopedia to enter the science topics they're interested in and automatically be driven to science locations or targets on Mars, locations on Mars where other scientists have found these topics of interest. For example, the scientists can type in hematite and find out this mineral, which is very interesting because it forms in the presence of water, what other sites scientists have talked about hematite in relationship to. Machine learning is used to triage the vast amounts of data that science instruments produce. In this case, visual transient events are being triaged using continuous quality control and retraining of random decision forests, allowing scientists to focus on the most relevant science events. The same technique is used to triage incredibly large numbers of radio science transient events, allowing the vast amounts of data that they couldn't possibly look at manually to be triaged down to a smaller number that they can focus on. And of course, deep learning is being used in a number of applications, and one of the most promising applications is to detect fugitive emissions, methane sources using remote sensing data. This is airborne data where they fly over different sites and they can detect things that are sites that are emitting methane, such as a fracking site or a leaky pipeline. And the deep learning has enabled them to detect much more faint concentrations of these substances. So one of the lessons learned here from NASA's applications are to focus on the value proposition. What are the high profile and most important applications where, if we improve the performance, it's worth the investment of applying artificial intelligence? And one of the biggest places of this is, in fact, in software, making the hardware better. We already have these tremendous instruments that allow us to produce these vast amounts of data. How can we best leverage the vast amounts of data we're producing? We saw this in the case of visual astronomy, radio astronomy, and all this airborne imaging spectroscopy data. We want to use artificial intelligence for even more ambitious explorations in the future. Take, for example, when Lewis and Clark went to the Pacific Northwest, they had much more limited abilities to acquire data and to store it in order to retain all of the incredible things they saw when they explored the Pacific Northwest. they traveled for 2 years, and they only were able to return with a handwritten journal of about 100 pages. Yet they mapped out this vast area, and they did this by figuring out a higher level language to describe things in. Their map describes things in terms of mountains, rivers, and lakes, and when they saw wildlife, they took samples and drew pictures. And what we would like is for our artificial intelligence system to go to an alien world and develop these kinds of constructs on their own. And what would it do? Well, the AI system would take the data and cluster it, and then instead of just sending back thousands of examples of each cluster, it would send back exemplars of those clusters, and then it would say, I saw data of cluster 1 in these, different areas, and just like the map of Lewis and Clark. And so we've actually started a program to study exactly this approach, and this is showing that approach applied to aerial data taken out from an airplane that was flying in a transcontinental flight. And the system clusters the data into different types of data, like cloudy data, rivers, mountains, and so on. And we compared it to data that was manually clustered by scientists, and there's actually a shockingly strong correlation. So again, this is the kind of thing we'd like to use to explore new worlds and new regions. And now I want to talk about how we want to search for life beyond Earth. So one of the things that's of great interest to scientists right now is the moon of Jupiter, Europa. And why is that? That's because on Europa, they believe that there's a sub-ice ocean, and the sub-ice ocean could have hydrothermal vents. That's very exciting to us because when I was a child, when I was a kid in the 1970s, people used to think, or scientists used to think, that life couldn't exist without light, without photosynthesis. But the amazing thing is they were wrong, and science has recovered from that. They discovered life at the bottom of the ocean, hydrothermal vents, surviving off of the different chemicals that happen when lava hits water, hits seawater. And we believe that ocean worlds, such as Jupiter's moon Europa, or maybe Enceladus, which is the moon of Saturn, might have these same hydrothermal vents, and might indeed be life there. So what do we want to do? We want to go there and we want to explore these ocean worlds, but it's very hard. We have to get all the way to Jupiter. When we get to Jupiter, we need to land on this icy surface, and then we need to melt through this ice cap, which might be 10 kilometers or more thick. Melting through that ice cap might take an entire year. And once we melt through that ice cap, we would deploy a submersible, and this submersible would go around and search and look for life, indeed, for these hydrothermal vents that we discussed. If you might think that this is all science fiction, it's in fact not. We are studying exactly what we would need to do if we were to conduct such a mission. In fact, in 2016, there was a cruise led by Antje Botius of the Alfred Wegener Institute, and that involved the Polarstern, a German icebreaker, and it involved Chris German of the Woods Hole Oceanographic Institute using this Nereid under ice submersible here, and Kevin Hand of JPL, the noted astrobiologist. And we too, the artificial intelligence team, we had a role in this as well. Our role was to study this human expert team of hydrothermal vent hunters and see if we could develop techniques that would be similar to what they would use. And in fact, we've done exactly that. This is actually a visualization of a search in a simulation. You can see the plume coming down here from the bottom. This is in fact the model of the plume. This is from the axial seamount, which is a hydrothermal vent off the Pacific Northwest coast. And we're doing what's called nested search, doing yo-yoing to try and find the plume. And that's in fact a technique that we would use if we were to be able to fly this Europa submersible. Another thing that we would like to do is we would like to find different features, like different fronts, and track them. And that's because these fronts are of great interest to the scientist. And so we've been doing deployments. This is showing the map from a deployment in 2017 off Monterey Bay. And this is actually what a vehicle would see as it swims these different yo-yos. And these different pockets change as a function of time. And we would want to have the vehicle detect them and then turn around and go back and forth in order to study these in greater detail. So this challenge of going to under ice oceans and to explore them and to find science features and to track them and to find hydrothermal vents is in fact a very active area of work and a fantastic use of artificial intelligence in my opinion. But what is the greatest challenge? Well, the greatest challenge is to conduct a mission to another star to hunt for life. This is very challenging, not just from a propulsion standpoint and a spacecraft standpoint, but from an artificial intelligence standpoint. The nearest star to our system, Proxima Centauri, is a little over 4 light years away, and it might take decades, 20, 40, 60 years to get there. When we get there, we can't really tell the spacecraft what to do. When we tell it, the signal won't reach the spacecraft for 4.5 years, and we hear back for another 4.5 years, so a total of 9 years. And if we were to go to the TRAPPIST-1 system, which is a system about 40 light years away, that's much more interesting. It has multiple planets that we know could harbor life. The travel time would be even longer, and the communications time would be even longer. What does that mean? That means it's this very complicated mission of searching for life, getting into orbit around planets, visiting them, studying them, maybe investigating their oceans, all has to be done by some kind of incredible AI in order for us to get the most effective mission possible. So I leave you with that challenge, the true challenge to go to another star system and find life beyond Earth as a tremendous challenge for an AI system. So I'm running out of time, so I just want to summarize by saying AI is already in use to solve many problems in space exploration and science. However, these represent a tiny, tiny fraction of the true uses of AI for space. And I want to leave you with the thought that AI is critical for future missions that will search for life beyond Earth. There's quite a bit of work. I just had a little bit of time to kind of touch on a lot of these things. If you're interested, there's many, many more papers and journal articles on these different techniques, not just at JPL, but at many other places. And I want to leave you with the JPL motto, which is to dare mighty things. Thank you very much for your time and attention, and I'd be happy to take questions now.
Steve, thank you very much indeed. We're going to open up the floor for questions, please, to Steve at NASA, live with us now from Pittsburgh. If you'd like to ask Steve a question, please just raise your hand and we'll get a microphone to you on this final session. Quick question for Steve. It's not often you get to speak to the NASA team here. Gentleman just there, thank you.
Hi, my name is Pradyumna. I just wanted to ask you, the mission to Europa that you described seems very exciting, but is there already a plan for such a mission or a timeline attached to it?
Oh, we've just lost your sound, Steve. Steve, bear with us a second. We're just checking your sound. Do we have sound?
Now we have sound. Can you hear me?
We've got you, Steve. Yeah, go ahead.
Okay, that's a very good question. There isn't a specific mission per se, but there are already teams actually in the United States and also in Europe. There's a project at the DLR, the German Space Agency as well, that's working on all of the different pieces that we're talking about. So there is a mission concept to land on Europa. There's a German effort to develop the drilling technology to get through the ice. There is a US study team looking at different technologies to drill through the ice at a number of different places. So there are people working on it, but there isn't a specific timeline. It is pretty far off. It's going to take, you know, at least 20 to 30 years to convince ourselves that we can reliably do all of these things.
Okay, Steve, thank you very much. We're going to leave it there, but thank you so much for closing day 2 of World Summit AI. I know you know it well. You were here last year, and it's wonderful to see you again, and keep up the good work at NASA. Steve Chien, everybody.
Thank you very much.